Hello friends, welcome to our channel Electronic Stuff. In my previous video, we discussed about Zener and avalanche breakdown. Today in this video, we are going to understand about tunnel diode. So here, tunnel diode is a heavily doped p-n junction diode in which current decreases as the voltage increases. And this tunnel diode is also called as Isaki diode. As in 1958, Japanese scientist Leo Isaki discovered that if a diode is heavily doped with impurities, then it exhibits a negative resistance in a certain region when it is forward biased. And such a diode is called tunnel diode. And here, negative resistance means the current across the diode, or we can say that the current across the tunnel diode will decreases when the voltage increases. And as you can see here, this is the circuit symbol of the tunnel diode. And the operation of the tunnel diode depends on the principle known as tunneling. And in electronics, tunneling means direct flow of electrons across the small depletion region from n-side conduction band to the p-side valence band. And we already discussed that p-type and n-type semiconductors are heavily doped, and this heavily doping results in narrow depletion region. Now let us discuss the working of the tunnel diode. So now at first, when the tunnel diode is unbiased, or we can say that when no voltage is applied across the diode, in that case the conduction band of the n-type semiconductor material overlaps with the valence band of the p-type material, and this happens because of the heavy doping. So due to this overlapping, when the temperature rises, the electrons tunnel from the conduction band of the n region to the valence band of the p region, and similarly the holes tunnel from the valence band of the p region to the conduction band of the n region. And here the noteworthy point is that equal number of electrons from n region and holes from p region will flow in opposite direction. So because of this equal number of electrons and holes, the net current across the diode will be zero. So we can say that zero current flows through this tunnel diode when it is in unbiased condition. So now here, when the small voltage is applied across the tunnel diode whose magnitude is less than the built-in voltage of the depletion region, then no forward current flows through the junction. And this is because no electrons can cross this depletion region. It means zero current flows through the diode. But however, few electrons from n region of the conduction band are tunneled into the p region of the valence band, and because of this tunneling of electrons, small forward current flows through the diode. So as you can see here, this is the VI characteristic graph of the tunnel diode when small voltage is applied. So here, when small voltage is applied, then small tunnel current will flow through the diode. Now here, when the voltage applied to the tunnel diode is slightly increased, then due to this increase in voltage, as you can see here, overlapping of the conduction band and valence band is increased. Or in simple words, the energy level of an n-side conduction band becomes exactly equal to the energy level of a p-side valence band, and as a result of this overlapping, maximum tunnel current flows through the diode. So see here, this is the VI characteristic graph of tunnel diode when the applied voltage is slightly increased. So when the voltage is slightly increased, so because of this overlapping here, maximum tunnel current flows through the diode. And now if the applied voltage is further increased, then as you can see here, a slight misalignment of the conduction band and the valence band takes place. But however, here the conduction band of the n-type material and the valence band of the p-type material are still overlapped. And because of this overlapping, the electrons will tunnel from the conduction band of n region to the valence band of p region. And because of this movement of electrons, the tunneling current starts decreasing. And if we go on increasing the voltage, then the tunneling current drops to zero. And at this particular point, the conduction band and valence band are no longer overlapped, and the tunnel diode operates in the same manner as a normal p-n junction diode. Now let us see the VI characteristic graph of the tunnel diode. So see here, at first if we go increasing the forward biasing voltage, then the current increases to its peak point value, which I represented as IP. And when we go increasing the voltage after this peak point voltage, then the diode current starts decreasing till it reaches its minimum value called valley point. And at this particular point, the conduction band of N-type and valence band of P-type are no longer overlap. So when we go increasing the voltage after this valley voltage, then the current starts increasing again as an ordinary PN junction diode. And here the region between point A and point B is called negative resistance region. And in this negative resistance region, as we discussed earlier, current decreases with increase in applied voltage. And now let us see some applications of tunnel diode. So these tunnel diodes are used as an ultra high speed switch, and tunnel diodes are used in FM receivers, and these tunnel diodes are also used as logic memory storage devices, and the tunnel diode can be used as an amplifier and an oscillator. So friends, this is all about tunnel diode. Thank you for watching. Please like and subscribe for more videos.